Have you ever wondered why certain metals emit electrons when light shines upon them? This phenomenon, known as the photoelectric effect, has been a subject of fascination and study among physicists for over a century. It's a cornerstone of quantum mechanics and has greatly influenced our understanding of light and matter. Let's delve into the laws governing this intriguing effect. The first law of the photoelectric effect states that the emission of photoelectrons is an instantaneous process, as long as the incident light has a frequency above a certain threshold. This means that the moment light hits the metal surface, electrons are ejected immediately, provided the light's frequency is high enough. There is no delay, no waiting period. It's a swift and immediate action, contrary to what classical physics might suggest. The second law, often referred to as the energy law, posits that the kinetic energy of the photoelectrons is independent of the intensity of the incident light, but depends on its frequency. In other words, cranking up the brightness won't give the electrons more energy. However, increasing the frequency of the light, shifting towards ultraviolet or even X-rays, will indeed make the electrons zip away with more gusto. This law challenged the wave theory of light, which predicted that brighter light should give the electrons more energy and help solidify the particle theory of light. The third law, also known as the frequency threshold law, stipulates that there exists a minimum frequency of light, below which no electrons are emitted, regardless of the light's intensity. This frequency is characteristic of the material of the metal. Even if you shine the brightest light possible on a metal, if the light's frequency is too low, not a single electron will budge. This law was a hard pill for classical physics to swallow, as it predicted that any light, no matter how low its frequency, should eventually knock out some electrons if only it's bright enough. Now, to summarize, the laws of the photoelectric effect tell us that the emission of photoelectrons is instantaneous. The energy of the photoelectrons depends on the frequency of the light, not its intensity, and there is a minimum frequency threshold below which no electrons are emitted. These laws, seemingly simple, had profound implications, challenging the classical wave theory of light and setting the foundation for quantum mechanics. The photoelectric effect and its laws demonstrate the dual nature of light, acting both as a particle and a wave. They highlight the quirky and counterintuitive world of quantum mechanics, where light and matter behave in ways that defy common sense and classical expectations. So, the next time you see light interacting with a material, remember the photoelectric effect and its fascinating laws. They're not just abstract principles, but rules governing the dance of light and matter, a dance that's happening all around us, all the time.